Hey Math 1, this is Mr. Roberts at Shasta High School. This is a quick introduction to sequences. A sequence is essentially a list of ordered objects, and you can see there's three different lists of ordered objects here. These list of ordered objects are often called terms or element, and in fact if I look at this, I would call this the first term, this is the second term, this is the third term, this is the fourth term, this is the fifth term, etc. Right? So you can see, again, there's three different sequences here. 1, 2, and then here's a third one down here. But all of them have a first term. All of them have a second term. I'll circle. All of them have a fourth term. I'll underline. I'm sorry, a third term that I'll underline. And all of them have a fourth term I'll overline. But those are the terms of the sequence. So for example, if I said, what's the fifth term of the middle sequence, we would come and we look at, this is the first, second, third, fourth. This, number 31, is the fifth term in the middle sequence. Let's just focus on that middle sequence because it's the type of sequence we're talking about today. This is called an arithmetic sequence. And the key feature of an arithmetic sequence is that all of the terms have a common difference. That is, they differ by the same amount. So if I look at the first term and the second term, they differ by 7. 3 plus 7 is 10. The second term and the third term, they differ by 7 also. 10 plus 7 is 17. The third term and the fourth term, they differ by 7. 17 plus 7 is 24, etc. Right? In each case, we're adding 7. Now, that's the key way of identifying whether or not a sequence of numbers is arithmetic. It is arithmetic if they have a common difference. And we typically use the variable d to denote the common difference between members of my sequence. I say members of the sequence, but I should also say the terms of my sequence to be more precise, right? So again, we're talking about the terms. Now, if I notice these numbers here along the bottom that are identifying which term we are, typically we use the variable n to describe those. So this is the, here n is 1 on the first term, n is 2 on the second term, n is 3 on the third term, n is 4 on the fourth term, n is 5 on the fifth term, etc. And if I want to talk about each of these terms' values, I can say this right here, a sub 1 represents the value of the first term. So a sub 1 literally equals the number 3. We can see it right up there. Let's talk about subscripts. It's really important that you exaggerate those. So when I say a sub 1, right, I'm reading it as a, the variable a, sub, which is short for subscript, 1, the value 1. Whoops. So be very, very careful. You don't want to write something like this. You don't want to write a1 because it just looks like a times 1. It's a subscript, which is a different sort of creature. So make sure that you really exaggerate that when you write them, right? A subscript 2, a subscript 3, a subscript 4, a sub 5, a sub 6. So if I'm looking at this sequence again without any ink on the screen, I could say, hey, what is a sub 5? What this question is what is the value of the fifth term in this sequence? And given this sequence, I can say, well, here's the first, the second, the third, the fourth. This is the fifth. So a sub 5 equals 31. For this particular sequence, the fifth term has a value of 31. Sometimes it's convenient to talk about the relative order of terms in our sequence without specifically talking about an exact value. So for example, I may want to talk about a sub n, term a sub n. Now, I don't know exactly which term this is. It depends on what the value of n is. For example, if n was 2, I would be talking about the second term, which has a value of 10. Now, if I wanted to refer to the next member of the sequence, right? That would, or the next term in the sequence, that would look like this: a sub n plus 1, you see. So for example, if n was equal to 3, and I was talking about the third term, a sub n plus 1 would be the fourth one, the one that comes after it. So this is kind of notation, and it's kind of tricky to look at, because a lot of times when we see this a and the n, we're assuming we're multiplying, or there's an arithmetic thing happening here, and it's not. It's just a variable, and it's a convenient way of identifying different members in this sequence. In fact, I could extend this, right? If a sub n is 17 and a sub n plus 1 is 24, I could also write a sub n plus 2. This is the one that's 2 away from a sub n. So I kind of talk about relative order here. There's two ways that we can define an arithmetic sequence, and both of them use this notation that we're talking about. And I want to help explain what this notation means exactly. This is called the recursive. This is a recursive definition. Let me write the word on the screen. C-U-R, C-U-R, and then we have a S-I-V-E. So this is the recursive definition of an arithmetic sequence. Arithmetic. If you're, if in home you might want to practice saying that word, arithmetic. Arithmetic. This is the recursive definition of an arithmetic sequence, and it uses the subscript notation that we just talked about. What this says is that the next term, the value of the next term in my sequence is equal to the value of the term that I'm at plus the common difference. Let me write these down. So if I look at this, this says the value of the next term, right, a sub n plus 1, is equal to the value of the current term plus the common difference for that particular sequence. So that would look like this in practice, right? Let's say that I'm sitting here at this value, and I want to know what the next value is. Well, this sequence says, right, this right here is my current value, and it says that this one, right, a sub n plus 1 is going to equal the value of my current term plus my common difference. The common difference for this particular arithmetic sequence, as we already discussed, is 7, because each time I'm adding 7 to get to the next value. So I would say plus the common difference d, but in this case I'm going to go ahead and plug in the value 7. So this next term, the value of the next term, is equal to the value of the current term, 24 plus 7. And you can see that, yeah, 24 plus 7 is 31. So indeed, the value of the next term, a sub n plus 1, is equal to the value of the current term plus the common difference. There are some sequences that we can only define using the recursive definition. But definitely arithmetic sequences can be defined one of two ways, always. The first way is this recursive definition, and the second definition is what we call the explicit definition. So this is the explicit definition of a recursive function, and it's a little bit different. One of the things that it makes reference to is a sub 1. This is the value of the first term. It also has d, which we know is the common difference. Every arithmetic sequence will have a common difference. And the notation lets me get at which particular value I want to find. And you can see right here it's with the subscript n. So if I want to find, say, the 50th term in a sequence, or the 4th term in a sequence, or the 5th, or the 1000th, I just put that value that I'm trying to find in the sequence in for n. So let's write the explicit definition for this particular arithmetic sequence. A sub n equals the value of the first term, 3 in this case, because our first term is 3, plus n minus 1 times my common difference. The common difference in this case is 7. We're still dealing with the exact same sequence. So if I go ahead and try to find this for the sixth value in my term, right? 1, 2, 3, 4, 5, 6. This would look like this. What is the value of the sixth term of your sequence? Well, because it's an arithmetic sequence, it'll equal the value of the first term plus 6 minus 1 times 7. Again, you can see the yellow here, right? N. I'm finding the sixth term. It's a sub 6, and then I place a 6 here. 6 minus 1 is 5, so this becomes 3 plus 5 times 7. 5 times 7 is 35, and when I add to that 3, I get 38. So the value of the sixth term of this sequence is 38. This is nice because I can verify it and see it in this case. Let's end with one final example. Here is an arithmetic sequence. I can verify that it's arithmetic by noticing that each time I move from one term to the next, I am adding 4. That means that D, my common difference, is 4. If I write the explicit definition, the recursive definition, this is the recursive definition of the function, I get the following: A sub n plus 1. In other words, the value of the next term in the sequence is equal to the value of the current term, where I'm standing at, plus 4 more. And I can verify that this works quite nicely if I'm sitting right here at the number 5, and I want to know what the next one is. Well, the next one is 5, the current one, a sub n, plus 4 more, 9. Let's go ahead and write the explicit definition for this for this arithmetic sequence as well. The explicit definition looks like this. If I want the value of any term in the sequence, a sub n, that equals the value of the first term. Here, the first term is 1, plus n minus 1 times the common difference. For this particular problem, the common difference is 4. There you have it. We have both the recursive definition of this sequence and the explicit definition of this arithmetic sequence. The secret word is tangerine.